Right, the last thing we have to talk about in this gargantuan of a unit in Physics 20, so it's finally coming to a close after oh so long, is power and efficiency. So power is the first thing we're going to talk about, and power has a really nice quick definition. It's the rate of doing work, so it's how much work you're doing per unit time. So mathematically, we could say that the power is work divided by the time. So power has this unit of W, work is still in joules, time is still going to be in seconds. So this W, this stands for the watt, named in honor of, go figure, a gentleman named James Watt. So breaking down the watt, you know me, I love breaking down units into fundamental units. No different here. So a watt is going to be a kilogram multiplied by a meter squared divided by a seconds cubed. A very helpful way, though not fundamental, to think about the watt. A watt is equivalent to 1 joule per second. This is a really helpful way to think about it, especially those of you that do Physics 30. This will be useful when we do electromagnetic radiation. Now, another way of writing this out, instead of having the work done, we also know through the work energy theorem that work is just the change in energy. So instead of having work here, we could replace that with the change in energy. So we could say that the power is the change in energy per unit time. Gives us the same thing. Back in the days, though, when we were doing stuff with work and we want to look at power, a lot of like, we'll call them, what's the word I'm trying to look for? A lot of, oh my goodness, I'm just losing my words today. Okay, sorry, there we go. Machinery. When we want to look at how good machinery was, we kind of compared them to horses, because way back when, horses were the, I guess the expression, the workhorses. They did everything. They did plowing, pulling, transportation. So comparing the effectiveness of your machinery to a horse was seen as a good measure. And that's where that unit of horsepower came to be. Now, those of you that are real auto enthusiasts, you know all about horsepower. Myself, not being a very auto-inclined person or know a lot about them, I don't know too much about it in that context. But yeah, the horsepower historically comes from kind of comparing machinery to actual horses and the work that they did. So by definition today, a horsepower, it's equivalent to 746 watts. Now, the other thing that we talk about when we deal with machinery has to deal with efficiency. So when you put, we'll call it energy or work into a system, we're going to call that your investment. Now, if you're inputting energy, you're inputting an investment, you would like to get the best out of that. You would like to get the greatest return on your investment. It's kind of like if you're putting in money. If you're investing money, you absolutely would like to get the greatest possible return on that money. Otherwise, you'd be a little bit upset because that's money lost. In terms of physics, when we're dealing with work and energy, we can measure that ratio of how much we get back to what we put in. And this is what we refer to as the efficiency. So mathematically, there's different ways we can do the efficiency. So we could talk about the energy output, so what we got out of it versus what we put in. Or we could do the power that's outputted versus the power that we put in. Those are common ways to express the efficiency. So the efficiency, when we do it this way, it's going to be a decimal value between 0 and 1. It can't be outside of those ranges. It can't be less than 0. It can't be greater than 1. But sometimes we'll express it as a percentage between 0 and 100%. If you're going to use calculations, though, you have to use the decimal form. You can't get around that. So we got a motor. It's rated at 5.60 kilowatts. Determine the work it can do in 20 minutes. Well, we know that the power is just the work divided by the time, or multiplying both sides by time here. We know that the work is just going to be the power multiplied by the time. Now, we don't want this thing in kilowatts, so we know we have this 5.60 times 10 to the 3 watts. We also don't like this thing in minutes, so 20 minutes is going to be 1200 seconds. Just make sure when you're calculating work, you want things to be in watts, you want your work to be in watts, you want your time to be in seconds. So this thing here, it's going to produce 6.72 times 10 to the 6. 10 to the 6 joules of energy. Now, what this is saying is that motor, so this is the work done by the motor in 20 minutes. In theory, the maximum amount of work it can do is 6.72 times 10 to the 6 joules. Now, it's saying that this motor, it actually only ends up doing 4.00 megajoules of useful work. So we want to find the efficiency of that motor. So this is kind of my output. this 4.00 megajoules, this 6.72 times 10 to the 6 joules, which is 6.72 megajoules. This is my input. I need to find the ratio between these two. In units, you're really flexible. All you have to do is make sure the top and bottom of your fraction have the same units. So if you want them both in megajoules, or if you want them both in joules, you just need to convert this into joules. So you'd be 4 times 10 to the 6. Either way, you'll be fine. So the efficiency, we're going to do the energy out versus the energy in. So my energy out is this 4 megajoules. And then input, I have this 6.72 megajoules. So then I'm going to get about 0.595. So what this is telling me is that my efficiency is about 0.595, or you might commonly see it being expressed as a percentage. Either way is fine. So we're going to say that this motor is 59.5% efficient. That's actually quite high. You might think, what are you talking about? Like 59.5% is not a high number. Relative to machinery, that's actually a pretty good efficiency. But that's a conversation we'll have to have another time. The last thing that we'd like to look at is we'd like to look at that relationship between power and speed. So if we have a motor, and I want to actually put here, I want to put this word instantaneous. So really what we're looking at is we're looking at the power at one snapshot in time. Back in kinematics, when we did things like instantaneous velocity and all that, those were looking at velocity in a snapshot of time. We're going to kind of do the same here. So if we have a motor, it applies a constant force to move an object at constant speed. We can relate our equations with work and power and speed. So we know that power is just the work done per unit time. And the equation that we have for work is we have that it's F equals D, F times D for our work divided by T. Now the force is what it is, but this D over T, if we're moving at constant speed, well, this is just going to be V. So the power at a particular point is going to be equal to the force that's being applied by some object multiplied by its speed at that particular point. So P is in, the power is still in watts, the force is going to be in newtons, speed is going to be in meters per second. So this only applies when the force and the speed are constant. So essentially here, you're going to need uniform motion. Now, you might see there's a contradiction. You might be like, well, Mr. O'Donnell, if there's a force, how can you have uniform motion? We're probably looking at the force on an object. Like the net force in this system is still going to be 0. But if the net force is 0, there can still be individual forces that make that up. So for example, if I'm looking at a car's engine, I want to look at the power of the car's engine. There's that force driving the car forward, but there's also a force of friction opposing it. So if those two happen to be equal, we'd have a net force of 0, be traveling at constant velocity. But I could certainly ask the question, what is the power due to the motor at this particular time? Because I know the force of the motor. I could find that, and I could also determine the instantaneous speed. So we have to be a little bit careful with this. So there isn't a contradiction. It's just kind of like when we did with work. We usually have to specify what's doing the work, or in this case, what's providing the power. If we were to look at the whole net system, then yeah, if it's traveling at constant speed, net force is going to be 0, so this wouldn't work. So we're just going to tie this off with the last example. So we have each car in a freight train, which includes the engine, experiences a drag force of 600 newtons due to air resistance. If the engine of the train is to pull a train of 75 cars, which includes the engine, at a constant speed of 72 kilometers per hour, determine the power required to move the train. So what we should probably specify here is this is the power of the engines. So if this thing is moving at constant velocity, there is certainly something that's going to oppose it. So we're going to condense the train down into a single point. So the whole train, it's certainly going to have a normal force. It's going to have a force of gravity. Now we'll say the train is traveling to the right here. There is going to be some force provided by the engines. So I'm going to call this F-eng, and then we're going to have this air resistance or this drag force. Now because this is traveling at constant velocity, the net force has to be 0. So when we see that constant speed, this is telling us F net 0. Really important. So what that is going to tell us in the x direction, the net force in the x direction, this F engine plus force drag, they are going to be equal because that net force has to be 0. So what we know here is that the drag and the engine forces are going to be balanced. So the force of the engine is going to be equal to the negative of the drag force. They're going to have the same magnitude. The negative just tells us it's going to be in opposite directions. Well, the drag force, we know that the drag force is 600 newtons on each car, and we're also told that there's 75 cars. So we're going to have that 75 cars multiplied by that 600 newtons. Now this drag force, I should probably also specify a direction. Oh yeah, I called right positive. So this thing is going to have to be negative because it's going against our positive convention. So that drag force, we want it to be a negative, and we're going to get it's about negative 45,000 newtons. So this is what's resisting the train. We have 45,000 newtons of drag force in the opposite direction of motion. So what we could say is that the engine's force is going to be the negative of that negative 45,000 newtons. Or we could say it's positive 45,000 newtons. So that gives me the force of the engine, and I would like to find the power due to those engines. So I know the force, and I also know that P is equal to FV. So if I know the forces provided by the engines, and I know it's moving at 72 kilometers per hour, which we're going to convert, that means I can find the power. We also just want to convert 72 kilometers per hour, which is going to give us exactly 20 meters per second. So my engine, it has a force of 45,000 newtons, and it's moving at a grand old speed of 20 meters per second. So what this is going to give us is this is going to give us a power output of 9 times 10 to the 5 watts. Now let's put this into context. What does this mean? What this is telling us is that our engine, in theory, it can produce a maximum power of 9.00 times 10 to the 5 watts in order to get this train moving. So let's look at the last piece of this here. So it's saying this engine, it operates at a really low efficiency. So it only operates at 15% efficiency. So we'd like to determine the power generated by the engines to move the train. What we'd like to find is we'd like to find the useful work. What we just found previously, the input work was this 9 times 10 to the 5 watts. We also know the efficiency is going to be the output divided by the input. So if we'd like to find the useful work, that is going to be our output here. Or yes, let me hang on a second here. Determine the power generated by the engines to move the train. Right, so we would like to find the output. Now, actually, sorry, let me rephrase that. Sorry, I just got this all wrong. Sorry, my bad on this one. I totally messed this one up. Sorry, if I go back here, this is the actual power that gets the train moving. So if the train is moving with this power, this is actually going to be the useful work. So because the train's actually moving under this power, this is the useful work that's being done. So what we're actually being asked to determine the power generated by the engines, we want to see how much power has to be generated such that when the efficiency kicks in, we get this 9 times 10 to the 5 watts. So sorry, this is actually going to be our useful work, and this is going to be our input work. So we would like to find the input. So for us, the input is going to be the output divided by the efficiency. Now the efficiency is given as a percentage. We'd like to make sure that it's a decimal, so we're going to say it's 0.150. So our output that we just found, output or useful work, that output work to get the train moving is this 9 times 10 to the 5 watts. We're going to divide that by the efficiency or our efficiency as a decimal. So this is going to give me 6 times 10 to the 6 watts. Again, I apologize for that. Sorry, I just kind of lost track of things here. So my input power is going to be this 6 times 10 to the 6 watts. What this is telling us is that this engine, when it's doing its thing, in theory, the maximum power it can produce is this 6 times 10 to the 6 watts. Once the efficiency of 15% kicks in, it can only do that 9 times 10 to the 5. It only has access to 9 times 10 to the 5 watts of power, and that power is what's actually going to get the train moving. So that's actually the useful bit that's contributing to the motion. And with that said, that is the end of our unit. Thanks for sticking with me on all of this.